it was at the end of a problem, so it shouldn't cause much of a problem. Just to remember that previous file is going to lose its functionality to some degree. You cannot do fast forwarding on it. Okay. Yes.
Is there ever a time where you use the conjugate of the numerator?
You can actually. It does show up in calculus, but
Then there's something online homework occasionally they do once you use the conjugate.
yeah. Let me.
I didn't know if it made that big of a difference.
Here, it's hard to sell. Why would you want to create something in a denominator? But that is actually how it shows up in your calculus 1 problem when you try to find a tangent line to, say, a parabola or something like that. That kind of an expression does show up. So something like this, simplify radical a minus radical b over, say, a minus b by rationalization. Again, the problem looks very artificial right now, but it becomes very natural as soon as you enter calculus. There you have to do the simplification becomes essential. You're trying to find the speed of something or slope of something. That becomes the natural step. You have to do that simplification for your answer to make sense and get the so-called instantaneous speed of a certain curve. Well, the idea is same as before, except that the place you apply it to is different. So what's the conjugate? Conjugate of which one? We multiply with the conjugate of the numerator. Let's just see what happens. Radical a plus radical b. So what is the result of multiplication of the numerator? Radical a times radical a is just a. Radical b times radical b, that's a b. The cross terms cancel. In the denominator, same thing showing up, and then you have some additional stuff. What happens? This cancellation that looks like somebody, a teacher, just insisting on something that doesn't bother you. It becomes essential in calculus where cancellation actually means something, and you get this answer, and that is a lot easier for you to digest over there than that, not just because of algebra, because of some other advanced issues. Okay, so idea of rationalization can be applied in also the format. The ones you almost see exclusively in these courses deal with square root. If you want to handle cube roots and such, the idea becomes a bit more complicated. You have to know some of those identities in college algebra. You don't practice all that much. Anyway, that was a side remark. Let's move on to some other examples here. Let me just ask you, for example, to see, I don't know if we did this yesterday or not, but from the same page, cosine of 83, cosine of 53, plus sine of 83, sine of 53. Again, the issue is to simplify, and by that we don't mean type this thing on a calculator. We want the practice on identity. This is one of those cases where you see the right hand side and you have to remember the left hand side, such as what? Such as you remember these identities. First you learn them, go from left to right, but in many applications you want to go from right to left. What does that mean? You see this format, and some red light should go off in your mind, say, oh, I've seen this thing somewhere. This is connected to that. That pattern recognition, that's how you solve problems. So here we come and say, this is cosine of what? 83 what? Minus 53. Okay, just there's a word of difference between plus or minus here. And you want to make sure that you get the right one. always, of course, use your calculator to make sure your guess is on the right track. Then you have to spend time. Cosine of 30, which is so I need to see this, I need to see this, and then I need to see that one. So that is how you show your progress. One reason we are limiting your calculators to the cheap ones is that they don't do that. But I wouldn't be surprised if by next year a $10 calculator will do that too. So in that case, I should just ban calculators altogether. Those fancy calculators you guys buy for $200 and they're more expensive than I don't have an SUV, but they're bigger than an SUV. They actually do this kind of things. But we do have software where these things are some of their features. You have access to them upstairs. If you want to work with them, Maple, Mathematica, and so on. There are free versions of those things. If you are interested, you can find links to them on my website. But yes, they are kind of moving everything from these books into these calculators. And there's a big debate if that's a good idea or not. But you go to the real world and come back and tell me in 20 years if that works. It doesn't work. I mean, I've seen surgeons and I've seen the professors and I've seen. You are going to see strange things. So, yeah, we cannot avoid education and say, okay, pressing some buttons is going to be replacement for a person who actually understands what's going on. I mean, the whole nation just lost $10 trillion. If it was that easy, how come these guys didn't see it? Actually, lots of people did see it. So they didn't even have to press a button. It was anyway. It's very easy to have wishful thinking. It's, okay, this doesn't matter, or that's why there are standards, so that you don't get into wishful thinking. Anyway, all this stuff is being recorded and I'll be in trouble. Let's move on to, let me see if you have questions from 2.1. I see some of these exercises I didn't do. Let's do, say, problem 65. Let's do one of those. It says sine of u is 3/5. U and v look too much like each other. Let me change the notation so that when you are reading this thing, you are not trying to check my handwritings. Sine of, say, alpha is 3/5, and sine of beta is 4/5, and alpha and beta in the first quadrant, what you are asked to find is things such as cosine of u plus v and other stuff like tangent of sorry for that. To answer your question, it's going to hunt me. It depends what kind of engineering discipline you go to. There is applied field activities where much of your activity is comes to you by experience and on the job training and such. And then there is the design side of engineering. In design side of engineering, you're creating things from scratch. It's not like some table that somebody already made that you go press a button or look it up. It's not a look up kind of a process. You are making it from scratch. And when you want to make it from scratch, you need to know, exactly what each tool does and what to expect from it, and so on and so forth. So the more you go toward the design and the theory and understanding the basics, the more of these things you need. The more you come to the applied side, then looking up and using a calculator will do. Both of them are respectable, both of them are needed. It's just that we don't know who goes where, so we are exposing a lot of kids to lots of things, and then later on you go find out what works for you. It's kind of like a Chinese buffet, like you go and figure out what matches you, and you take it from there. Now, now this problem is a little bit overly simple, and simple problems tend to be confusing. It's simple in the sense that this alpha and beta happen to be kind of sisters or complementaries and such, so it might leave you a wrong impression in you. Anyway, how do you handle this problem? What we want to do is to get cosine of alpha plus beta. We have to know the identity. Cosine of alpha plus beta was cosine of alpha, cosine of beta, and what was the other piece of it? Minus sine alpha, sine beta. Okay. I have some pieces of information. I have sine alpha, I have it. Sine beta, I have it. But how about cosine alpha, cosine beta? We can get those things one of two ways: by drawing pictures and triangles and working your way to that answer, or using identities. Perhaps pictures are easier for this one. How do we make a picture? Say sine of alpha is 3/5. Tell me a nice triangle where that fact is shown. So I pick a triangle alpha, and you tell me how to label the sides such that the sine comes out to be 3/5. 3, 5. This is going to be 4, of course. So how is that useful? Well, sine is given, but cosine is not given. But you come from your picture, immediately find out what the cosine is going to be, which in this case is what? Cosine of alpha. You say cosine of alpha is 4/5, so this is 4/5. Cosine of beta. Well, I have the sine of beta. Again, I said this is a coincidence in this problem that the numbers are the same. Here's your beta. Give me the side of this such that it matches the given information. This has to be 5, and this one this time becomes 4. Again, coincidence that these are looking like each other a lot. Anyway, cosine of beta, I need that too. 3/5. So it becomes 4/5 times 3/5 minus sine was 3/5, and sine of beta was 4/5. What is the net? 0. And that's what we were asked to find. What is cosine of alpha plus beta? It turns out to be 0. If we were a little bit awake, we could have said from beginning this alpha and beta are going to be complementary. Their sum is 90 degrees. Cosine of that is 0. Could have bypassed a lot of that. But that's pure coincidence. I think the book didn't mean it. It just happened to be like that. Well, you need to give me the detailed numbers, and then I'll there are a few typos here and there on the software. Yesterday, Sarajin mentioned one of them to me on problem similar to problem 7. There is a sign problem there. Plus or minus on it seems to be off. But some other problems here are in preparation for more identities coming up. 73. So it's just pushing you to create those identities yourself. Sine of alpha plus beta plus sine of alpha minus beta. It is asking you to simplify, to clean this up. Amazingly enough, that's an identity that comes up when you study music. So if you play two tunes simultaneously, you get a special effect on a piano or something. You get a hum and a buzz working at the same time. Explanation of that requires this identity. And those of you going to engineering, you are going to see that 2 years from now. But anyway, right now we just open this thing up. We say this is, sine of alpha cosine beta plus cosine alpha sine beta. That is this portion. Then I keep going. Sine of alpha cosine beta, this one comes with a negative. Cosine alpha sine beta. So what happens? We double up on the first term and the second term. They are going to cancel each other out. So these two become a net of 2 sine alpha cosine beta. So on the start, first of all, we said sine and cosine trig functions are used to represent waves. One of the simplest waves are the sound waves. These are pure sound waves like the harmonics you play on a piano or a musical instrument. Having two of them is like you are playing two notes simultaneously, or you have two tuning forks and playing both of them simultaneously. You get a special combination of those two sounds. When you want to understand what is going on, you are going to need this identity that tells you how the two sounds sometimes cancel each other, sometimes reinforce each other, and so on. Okay, so that was an example there. Before we go to section 2.2, problems from page 114, they tend to push you to understand what you have done a lot more than what we are doing here. In the first reading, perhaps you skip that, but many of these problems are important. Like problem 91, that's preparing you for calculus 1. It's asking question. It says take the function f of x is equal to cosine of x. Simplify f of x plus h minus f of x over h. In calculus, this is the beginning of a discussion of how fast does this function change. When you want to know how fast does something change, you change the input, you get the response of the system, see how much the system changed, you divide by how much you change the input. It's like if you have a knob on an instrument, you change it a little bit, you see what happens to the instrument. This function is your instrument. The input of it is the knob that you control. So here the knob is x, here the knob is x plus h. The knob has moved over by h. You make the function change by that amount, the input to change by that amount, and you measure the change in the output, take a ratio to see essentially a kind of a sensitivity analysis, a ratio of the change of output to change in input. Over there you call that speed or various other terms. Okay, here we go with the precalculus or trig component of that question. Cosine of x plus h minus cosine of x over h. So our f is that function cosine. We have changed the input from x to x plus h. Question is, how can we rearrange this thing so that we can do further analysis? This portion of it requires the trigonometry you are just doing. You say cosine of x, you tell me what's the next piece. Cosine of minus sine of x, sine of h. Okay, this is as far as trigonometry goes. Then in your calculus they say, well, let's break this up into two portions. First, I'll match up these two terms, and then put that one separately. So that is going to look like this. Cosine of x, cosine of h, minus cosine of x, and then I'll have minus sine of x, sine of h, whole thing divided by h. Now, for a reason that you are going to see later, they just rearrange this thing a little bit more, meaning we are going to break it up into two pieces. Here's one piece, I just have cosine, and here's another piece, I just have sines. So I take that, say cosine portion, I have a cosine factor. I factor cosine of x, I leave everybody else in a fraction. Now you help me out and tell me what's going to be left after I factor cosine. Cosine h, and from here a minus 1 is going to be left. I remove sine ahead, and essentially I'm separating h from the x. H was the amount by which you change the knob. What's going to be left in this fraction? What is numerator and denominator of this one? Sine of h over h. And then your lecture in calculus is going to continue with the further discussion of what happens to these things, what is so significant about them. There is significant discussion after this. But right now the problem in problem 91 is just asking you to see how this thing come about, and so on. Let's take a 2-minute break, and then we are going to continue. So we are going to section 2.2, taking a look at some of the half-angle identities. Let's just quickly remind ourselves what some of these identities were. Suppose what do we remember for cosine of theta in terms of double of that angle? Do you remember? How did I write it? Let me write it the same way so that it doesn't become additional issue here. Let me just quickly list these identities. We had sine square of theta was 1 minus cosine of 2 theta over 2. We had tangent square of theta was 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. Previously, I might have taken a square root, that is, on the previous lecture, it might have shown up like this. Or it might be written like this. So you need a comfort level with the algebra manipulation here to make sure that you don't get overwhelmed by all these quick changes here. What else did we have? Check to see if it's time for my retirement yet or not. Let's see. Maybe I can push it one more year. Okay, so let's okay, we just briefly mentioned what are the tools of the trade in this section. Picking up one of these questions, one question is, what is sine of 105? So here the emphasis is find sine of 105 using half angle. We just did a problem like this using some difference formulas. So if you are comfortable with the double of this angle, perhaps that is going to give you a clue about the angle itself. Now, do you feel comfortable about double of this angle? What's the double of this? 210. Is 210 easy angle to deal with? What's the reference angle of 210? Where is 210? So here's 90, 180, 210. So is that the easy angle? 210 has a reference angle of 30. So finding its sine, cosine, tangent, and such will be straightforward. So that gives us an idea. If you want to find sine of 105, we come and say, first, figure out sine square of 105. Sine square of 105 by this identity is 1 minus cosine of what? 210. Very good. So if I figure that out, I can figure out sine of 105. So we divert our attention to cosine of 210. Cosine of 210, first of all, it is in which quadrant? Third. On third quadrant, cosine is positive or negative? Negative. What was the reference angle of it? 30.
I have a question about
Yes.
that. Okay, because when do you know to, so you would just subtract it from 180? I mean, yeah.
So you say 210, it passes 180, it comes to the third quadrant, but doesn't pass 270. Is that right? So it's stuck in the third quadrant. I say, how far is it apart from the horizontal line?
Okay.
Horizontal line is 180. I take that angle, say 210 minus 180. I have crossed by 30 degrees. So my reference angle becomes 30.
Okay, so you always subtract it from the one it's just passed?
Mm-hmm.
The one that it could.
No, not where it's headed to, but the horizontal line that it just crossed over. The nearest horizontal line that it crossed over, that's what gives you your reference angle. And you calculate based on that. So we say reference angle of this is 30. It's in the third quadrant. So that settles for me what this is going to be. What's cosine of 30? Okay, so by now we have the following. Sine square of 105 is going to be 1. Tell me what to write next. Minus cosine of 210, which itself was minus radical 3 over 2. Whole thing over 2. Now help me clean this up a bit. It's 1 plus radical 3 over 2 over 2 again. Can you clean up that complex fraction for me? If I take a common, what's a combined denominator of these two? Okay, let me write it out then. So take a common denominator 2 plus radical 3 over 2. How do you divide a fraction by a number? So you say, think about this as 2 over 1 multiplied by the reciprocal of this. So we have 2 plus radical 3 over 4. So by now, what we have is sine square of 105 is 2 plus radical 3 over 4. Now, what is sine of 105 itself? What should I do to this thing to extract sine? take square root of it. Is that right? So I have to take a square root of this whole thing. But here's a challenge. Should I put a sum or difference? Excuse me. Should I put a plus or minus? Well, that decision, you remember the way these formulas were written, we had them like sine of theta is plus or minus radical 1 minus cosine of 2 theta over 2. And over there we left the decision of which one of these two signs you are going to pick based on where the angle itself is. So 105, which quadrant is 105 in? 105 is in quadrant 2, is that right? So sine is positive there. So out of these two signs, which one of them should I work with? Positive. So we got this answer. Of course, if you go back and check the answer we have gotten previously using sum and difference formulas, they look different. Let me see if anybody can pinpoint why are they what I'm trying to get at. Okay, we have finished this problem. As far as the book wanted us to figure out sine of 105 using half-angle formula, that's the answer. But a careful student is going to say, I just did same thing in the previous section where I said 105 is sum of which two angles? 60 plus 45, is that right? Over there the book told me calculate sine of 105 using sum formula. So this is sine of 60 plus 45. What was the sum identity? Sine of 60, you tell me what I write next. Sine of cosine of 45 plus cosine of 60 sine of 45. Well, what is sine of 60? Radical 3 over 2. What's cosine of 45? Radical 2 over 2. Cosine of 60? Sine of 45. So when you boil this down, you get 4. This is radical 6 plus radical 2. Now I want to hope that some of the students in this course will try to figure out what happened. This is, and I got that one over there. What's going on? So let me put that as an open question here and keep going with the other main agenda that we have, figuring out two answers. They look okay. In your software, they just insisted that you take this 4 out. If you take the 4 out, what do you get? These are called nested radicals. Interesting topic all by itself. We have a radical inside of which there is another radical. But this 4, we could take it out. That would be a simple issue. Gives us a 2. Okay, so in that section, that's what the book was expecting you to type in. And another question, another request is find out tangent. Yeah. Here we are using the following rule from algebra. If you have radical A times radical B, you can say everything positive. This is perfect game. If you have a ratio, radical A over B, you can break it up to radical A over radical B. So with these basic rules that we have, here you have radical. This is your A, this is your B. We say, if you wish, let me make some room here. this, according to that, can be written as square root of the numerator over square root of denominator. So a square root of a ratio can be written as square root of numerator over square root of denominator. That one, it's a bit of a challenge to do anything with it. I left it to you to do that. That's a little bit advanced. Radical 4, well, you just substitute 2 for that. We are all set. Okay? And the software would have accepted this. Next question that you had is, how about tangent of pi over 8? Of course, radians. What is pi over 8? Well, we know pi over 4. Pi over 4, that is 45 degrees. What is pi over 8? A thinly sliced pizza is going to have 16 slices to it, each of them 22.5 degrees. So what this problem is asking us to do is, so to get an idea of what angle we are talking about, each of these things is pi half. Now I have pi fourth. So this was pi half, and then you got pi fourth. If you insist on doing this thing, this is going to be pi eighth. Question is, can you give me the description of that angle? Yes, we can do, so long as you take something that is well known. You cut it in half, we can give you all the description of that half thing. If you keep doing this, we can still go. Expressions are going to get kind of messy, but we can do. Like if somebody was interested in pi 16th, pi 32nd, and so on, those are all accessible with exact description. Okay. What were the half-angle identities we had for tangent? So if you have an angle, tangent of an angle, you want to convert it to, you want to write it in terms of double of this, you had many choices. Some of the choices that didn't involve radicals were what? They might be more comfortable to use. Okay, so perhaps you saw the formula like this. Tangent of x over 2, what was that equal to? Sine of x over 1 plus cosine x. Or if I start with theta, my starting angle being theta, what do I have on the right hand side? Always remember, this is double of this angle. So this is twice theta, so 1 plus cosine of twice theta. These are saying the same thing. Everybody says that. So long as this is half of that, we are safe. Well, if I want tangent of pi over 8, what does this tell me to do? Take the sine of what angle now? What is double of pi 8? Pi 4. 1 plus cosine of. Now, pi 4, we know from experience what that one is. What is that? So I can multiply by 2. So what I just multiply by the LCD. Multiply everybody by 2. That's the easiest way to clean up all the denominators. LCD of all of our fractions is 2, so I multiply by that. Then this is 2 plus radical 2. That might be fine for some. Some might insist on, no, you have to kind of judge what the format the book wants. We do rationalization here one round. So what do I get? 2 times 2 is a 4. Radical minus 2. On the numerator I have 2 radical 2. Radical 2 times radical 2 is minus 2. So I factor 2 times radical 2 minus 1. On denominator I have 2. When I knock this out, tangent of 22.5 degrees, we have the following clean-cut expression for it. So to see more of these examples, you'll go to problem 17 through 22. Make sure you do a couple of those. Okay. Any other questions from 2-2? From 2-2? Are you asking about this one? Okay, we say this is different. It's a difference of squares. So you can factor it as difference times the sum. Everybody with me there? Like if you add a to the power of 4 minus b to the power of 4, you could factor it as a squared minus b squared times a squared plus b squared. Now, this in trigonometry, we have this special situation. What is that? And we had this in our identities. What is that one? Cosine square of x minus sine square of x. That's where that practice comes from, that you write the one side of identity, try to guess the second side, and next time around you write the right hand side and try to guess the left hand side. This is just cosine of 2x. So what we have is that expression is just cosine of 2x. Any other question from 2-2? Make sure you take a look at problems from 41 through 48. These are just exercises on, the book calls them skill maintenance, like from the previous section. These are basic identities being repeated here again. Okay.
What identity is that? It's cosine square x minus sine square of x is the equivalent to cosine square of x?
Is equal to cosine of 2x. You didn't see that identity? That is like on top of a page 119. Okay, how about a few graphing questions or anything from chapter 1, 1516. So remember your test is 1, 5 through 2, 2. So we did some exercises on graphing which was concentrated on shifting, scaling, and such. Make sure you know the very basic function, the basic definitions, amplitude, period, asymptotes, turning points, highs and lows, crossing points. So that's how we talk about the graph of these functions. We have, so if you have a graph of a sine, this one we call it one cycle of it. If I want, say, 2 cycles, you go here, 2 cycles of it now. It has an amplitude. It has a period. Questions could be related to using degrees as unit or radians as unit. So this could be 360, could be 2 pi. We talk about crossing points like 0, pi, 2 pi. We talk about turning points here, pi over 2, 3 pi over 2. Other terminology used, this is referred to as a maximum, this is referred to as a minimum, or high and low. And this line is referred to as the midline of the picture. So if I were to ask you y is equal to 2 sine of x plus 3, I could ask for the sketch of it, and then I could ask for transformations in order that if you apply to that, you get your final answer. We had several types of translations and transformations. Let me put a minus here just so that we cover all bases for this one. What kind of things do I need to do to this function to get my final picture quickly? So however you sketch it, you can go ahead and sketch it, but also insist on a description of what kind of transformation actually creates the final answer quickly. So we'll go and look at the amplitude. See, what am I doing to the amplitude? What am I doing? 2 things. Flip across the x-axis, so reflect, double the amplitude, or scale vertically by a factor of 2. Now, whichever of these you do first, that's fine. You can stretch it and then flip it over, or you can flip it over and stretch it. So here we flip over, that's picture number 1. Then we stretch it, that is picture number 2. Then what do we do? What's the role of this 3? Step 3, raise or shift up by 3 units, or you can say midline goes up 3 units. So if this is 1, 2, this is 2, well, and 3, so my midline is going to be here, and the picture is going to oscillate around that one. So it's going to come 2 units below this, something like that. So what we said, 3 actions. One is a reflection, one is a stretch, and one is a vertical shift. That guy comes last. You do either of these first, a reflection and a stretch, and then a picture is going to move up by 3 units, and then you're all set. Now, we didn't do enough exercise of the other type. Make sure you don't miss that. So if I have a picture like y is equal to, say, cosine of 2x plus 60, and here the implication is that we are working in degrees. Sketch, list transformations. Transformation, we said the order in which you do them, transformations that are in the same axis, they can interfere with each other. So it becomes important which one you do first. These questions you might be asked to specify amplitude, period, phase shift, and so on. What's the amplitude of this? Amplitude hasn't been touched. Amplitude is 1. What is the period of it? If I double the x, what does that do to the period? Say it again. Period becomes 180. Is that right? When you double the x, things are running faster. Your period becomes 180. What's a phase shift? How much has the graph, the way it's defined in the text, how much movement, horizontal movement do we have, in which order and which direction? Do we go right or left? Left. Okay. Phase shift is minus 30, negative ratio of this to that. Okay, how do we go about graphing this? You start with the very first picture. You label your picture according to degrees. So by the time we are finished with one cycle, we have gone through 360 degrees. Actions to be carried out. What does that 2 going to do to us? We say shrink or compress horizontally by a factor of 2. What does the book call it? When you compress, but the book doesn't call it anything. Shrink. Yeah, that's exactly what I said. Shrink horizontally by a factor of 2. So what does that do? Whatever you had at 360 is going to now show up at 180. So everything is going to happen that much faster. My picture is kind of a bit of a rush here. So far all I got is cosine of 2x. Next, I'll have the influence of that addition of 60. What is that going to do? Last in the list of things we do is we have a shift of 30 degrees. So these points that were at, let me mark them. This was at 45. This is 135. We are going to move left by how much? 30. So my cross, you have to specify the crossing now. Where is the start? Start at minus 30. Is that right? Because we moved left 30. My first cross is going to come to what point? 15. This becomes 15. So I start from here, come down at 15. My low point, which was at 90, is going to shift to where? 60. this picture got really bad, but the crossing point, the next one was at 135. Where is that going to go? 105 somewhere. And the high was supposed to arrive at 180. That's going to be now at 150. So that's going to be one cycle of cosine of 2x plus 60, and then that's set you off. So make sure you do a few exercises of this type, and that should be. So you practice all of your identities. You write and rewrite that. A substantial portion of your grade on the test comes from duplication of those identities. Next, you do a few problems from each type. Review the videos and the problems in the text. You'll be okay.